So our next speaker, if you were here for Roger and Youngday's talks yesterday, you will have seen his name popping up on their slides quite a bit. So Syed Rafiul Hussain is an assistant professor with Penn State University and a leading mobile wireless security research expert.
Thank you. Hello, everyone. It's my pleasure to talk about our research on 4G and 5G cellular networks, or next-gen networks. And I really appreciate Paul, Ismail, and the whole SRS team, because when I was a PhD student, my whole PhD research was revolved around this cellular network and srsRAN. And I'm really grateful that I got a chance to play with srsRAN, which actually gave me the foundation of my research, the PhD research, and all the follow-up work. So let's get to the discussion today, like security by design for cellular networks. I'm an assistant professor again, and I lead the systems and network security research group at Penn State. So, I mean, most of us today, we have talked about 5G or Open RAN. So mainly I will give more like principal approaches that we can use to secure 5G or similar systems such as ORAN. So let's first take a look at that why cellular networks are not yet secure. So when such kind of complex network systems are developed, first we consider functionality, that functionality should be there, performance, and security comes at the very end. In fact, when cellular networks was first designed, the first generation, there was no security at all. There is no concept of adversary. Even up to 3G, that means until 4G, we did not have any kind of mutual authentication between the user devices and the network. Now, to see that what went wrong for such systems, let's take a step back and see that when the networks were designed, inadequate security analysis early on the design phase, they missed what are the security and privacy guarantees or the specifications like 5G or ORAN specifications. They have so many inconsistencies, ambiguities. Like, in fact, if you see the ORAN specification, there are a lot of things that are still evolving. In fact, many of the things are still like under-specified. 5G is more mature, but ORAN is getting more matured. But hopefully, I mean, if we have this like evolvement and if we have design phase security, then it will be good. But anyway, like lack of this kind of security analysis early on the design phase, they may cause many design level vulnerabilities. And all these design level vulnerabilities, they eventually go down to the implementations, because all the deployments, 4G, 5G, ORAN, whatever deployments you can think of, like ORAN SC or SD-RAN, they actually follow the specification. And all these design level vulnerabilities, they will go to the deployments. But this is not the end of the story. Deployments, they sometimes oversimplify some of the complex protocol interactions. They sometimes the specification, they specifically leave the choices to the developers. They sometimes did some mistakes when choosing the directions, and sometimes there are poor input sanitizations. So we have implementation level vulnerabilities. Now, this talk will focus on that all these problems lead to different vulnerabilities, but mainly what I'm trying to focus is that this talk will show that how we can incorporate secure by design principles for developing next-gen networks. Next-gen means that 5G and beyond, and also similar kind of complex systems such as ORAN. So mainly I'll be focusing on the first, two of my recent work. First one is the adversarial testing framework for analyzing the design of 5G cellular networks. The technique is applicable for 4G. Technique is also applicable for analyzing the ORAN specifications. Mainly, we are focusing on adversarial testing or security analysis. So our main focus is on analyzing the security and privacy properties. The second phase, second part of my talk, I'll focus on given the your baseband implementations or UV implementations, how you can create an automated approach to analyze the security of those baseband implementations. So this is the problem statement for the 5G reasoner, that how can we systematically verify the design of 4G and 5G network protocols with respect to the promised security and privacy guarantees. So I'll show the general principle, general architecture. Then we'll briefly discuss that how we can instantiate for not only for 5G, but also for ORAN. So the high-level goal of this problem is to build an automated reasoner that will take the design specifications and the security and privacy properties, and that will tell, this automated reasoner will tell whether the property or guarantee is satisfied or not. If the guarantee is broken, then how the attacker can exploit that missing guarantees. But to develop such kind of automated reasoner, there are many challenges. Mainly the first challenge is complexity of the protocol, 5G protocol or RAN protocol, whatever protocol you can think of. First of all, these are stateful network, and they have cryptographic constructs, means that it's not about just sending or receiving messages, but the message could be encrypted, message can have integrity protection, and so on. So the automated reasoner that are available so far, some reasoner work for only stateful networks. They don't work for cryptographic constructs. And some other reasoner, they are very good at reasoning cryptographic constructs, such as whether the encryption is correct or authentication is correct, but they cannot work well for large or complex stateful networks. They only work for very minimal size of protocol. Second challenge is that in cellular networks, we have many different participants, such as you have the phone, you have the base station, and the core network has many components. Now we have ORAN, right? So there is another module. And all these protocols that we're talking about, for example, registration, deregistration, mobility handoff, all of them are intertwined. And the properties that we want to test, the security, and privacy properties, they are of two types. One is the qualitative properties, another one is quantitative properties. Qualitative property, an example is that, let's say, after authentication, I can only access my network, right? So authentication should come first before you can access any resources of the network. Quantitative properties are mainly about, like, let's say, average number of messages you have received. I mean, those properties are mainly used for analyzing the performance, but there are some other security-related properties that are dependent on also quantitative properties. So at the core of our reasoner, we use model checking. So I'm trying to give a very high-level idea about model checking. So by model, we mean that abstract behavior of the system. It's not machine learning model. It's a logical model, mathematical model. So you abstract the protocol behavior into this mathematical model. You can think of it as it's a glorious form of graph or finite state machine. Now, you have the security and privacy properties that are represented here as phi. And the model checker takes this graph and this property, and it checks all possible paths in this graph to find where the property or security and privacy property can get validated. So it does automatically, okay? The model checker explores all possible execution path automatically. And if there is no execution path where the property is validated, that means the system, the property is, the model is verified against this property. Otherwise, we get a counterexample. This counterexample means that from the starting of this graph, the entry node, to the node where actually the property got valid. So we get a trace, and we call this counterexample trace. That means the attacker can follow that trace and perform an attack that violates the policy. So of course, like we consider over-the-air attack mainly. And for over-the-air attack, we assume that the layers inside of your device, your UE, they are securely communicating. Also, the base station and the core network, we assume that since they have more security protections, for example, IPsec tunneling protocol and so on, their communication is secure. So we consider that the adversary can interfere the communication channels between the device and the base station. Now, this is the key insight of our tool, that the properties that we want to check or verify, they have certain characteristics. First one is the temporal ordering of events. I said earlier that authentication should come first before you access any resources of the network. Second one is the cryptographic constructs. For example, authentication, encryption, observational equivalence. And third one is the linear integer arithmetic. For example, you have, whenever you send a packet, you have a sequence number, you keep incrementing that sequence number to make sure that no replay attack happens. Now, the key idea here is that the off-the-shelf model checker they are good at reasoning only temporal trace properties and linear integer arithmetic. But on the other hand, cryptographic verifier, off-the-shelf cryptographic verifier, they can efficiently reason about the encryption authentication properties. But I mean, they have their own shortcomings. The key idea here is that how can we leverage the reasoning power of these two? So we combine them and create the adversarial testing framework called 5G Reasoner. So here is the architecture that we have the technical specifications, 3GPP technical specifications. If you want to analyze ORAN, let's say ORAN design, all the like specifications, you can also replace these 3GPP specifications with ORAN specifications. So here we manually read all the specifications. It's a huge manual task. I'll show later that how we can remove this manual task and make it automated. Like we read all these technical specifications and create these glorious form of graphs or finite state machines or model, and we combine them and call abstract cellular protocol model. So here, it actually captures all the protocol behavior of the EV, base station, RAN, and the core network. And we say abstract cellular protocol model. And one thing that we simplify here is that we remove all the cryptographic related constructs. For example, if a message has encryption, we remove that. I'll tell that why do we do that. So we feed that, we incorporate the adversary model. So we can instrument the model and so that what are the adversary can actually influence. And get the threat instrumented model, and then we feed that to the model checker. And from the technical specifications, we try to extract some of the properties and feed that properties to the model checker. So this is the first part. Model checker will find that whether any counterexample, is there any execution path, whether the property is validated or not. If not, good, satisfied. If yes, validated, then we get a counterexample. But the counterexample could be spurious, could be false positive. Why? Because we say that in the previous slide, that abstract protocol model here on the left, bottom left, that we have actually simplified. We have replaced all the cryptographic related messages with their plain text counterpart. Now, we have to see that this counterexample is a real counterexample or not. So what cryptographic protocol verifier says that whether any of these steps in the counterexample, that is any of the dot sign in the counterexample, those are called steps, whether those steps can be executed by the adversary or not. That means, if any assumptions are validated with the respect of cryptographic assumptions, then it is a problematic. If any of the cryptographic assumptions are not validated, then we consider that as an attack. We take that to the testbed we developed using srsRAN and confirm that yes, this counterexample is feasible for the attacker to execute. Then we call it an attack. Otherwise, if counterexample is spurious, we feed that as a feedback to the model checker and say that, hey, this counterexample should not appear in the next round. So this is the main idea. For the sake of time, I will skip the example part. So this is how actually step by step how model checker and the cryptographic verifier works together. So overall, we instantiated this 5G reasoner framework for 5G. The previous version of the 5G reasoner was called LT Inspector. And with 5G reasoner, we uncovered 11 new vulnerabilities and 10 new vulnerabilities for 4G. So some of the implications of these vulnerabilities are authentication bypass, location tracking, your temporary identifier exposure, denial of service attacks, and some of the artificial chaos. I know that many of the cellular hackers who already know that the artificial chaos, but I am going to show you a demo for the general audience. So here in this demo, I'll show that how the attacker using a, very low cost software-defined radio and using srsRAN can launch an attack against commercial networks. So here, assume that you have a, this is the software-defined radio, and with srsRAN, we have created a fake base station, and we are trying to inject a emergency alert message to the LTE UE connected to the LTE network. All right, sorry about the weird sound. So it just sends an emergency warning message, active shooter, stay safe. You can actually inject any kind of emergency and tsunami alert messages or Amber alerts, right? So this is one of the easiest attacks that we have found through this analysis. Anyway, so this is the using this software-defined radio, attacker is injecting these messages to a device which is already connected to a actual base station. I mean, actual base station means that regular base station. All right, so let me then quickly switch to the next part of my talk, which is the stateful security analysis for baseband implementations. So we know that 4G, which has been the de facto standard before 5G, and it has been supporting 5.8 billion 4G devices, which is operated by 807 network operators worldwide and in 170 countries. Now in 5G, it promises to support trillions of 5G devices, which will enable a lot of other services such as Internet of Things, autonomous vehicles, supply chain management, autonomous healthcare, and so on. So 5G devices is very critical. And if 5G devices are not secure, that can be an initial infection point for the whole networks. So what we want to say is, emphasize on that is that analyzing the security and privacy of cellular basebands, which is the cellular modem, is very important. Now, how to analyze? The cellular basebands should comply with the specifications, right? Any deviations, if the developers or vendors, they deviate from the specifications, those deviations may cause some exploitable attacks or may cause some performance issues, such as interoperability issues. Now, the question is that whether we can build any automated framework to analyze their security and privacy of 4G and 5G basebands. But the challenge is that we have a specification, but that is not formal. So it is a humongous manual effort to make it formal. Now, there is also no formal implementation or baseline to which you can compare your developer built basebands. Also, this system is black box because even though most of the time the binaries are available, it's very hard to analyze. And all these implementations, protocol implementations implemented in the baseband, they are stateful. So there are some approaches, great approaches, but they have also some cost or limitations. For example, rehosting or reverse engineering the basebands. It was done by Grant. I know Grant is here. So it required him, I know that even though I didn't talk to him before, I know that it took a humongous manual effort. It's not engineering effort. It's not underappreciated. It's a really appreciable work. But to make it generalizable for other basebands, let's say he did for 2 vendors. But if you want to generalize for multiple vendors, more vendors, it is really difficult. So another approach done by Yangdai, LTE fast and dual LTE test. These are great, but they have also some limitations. For example, they are stateless testing, and also sometimes they do handcrafted test case generation, which is not so much efficient. So we propose that DIQE. So DIQE, let's not go into the details, but DIQE takes all the basebands of different vendors, and the idea is that it will apply some differential testing. Since we don't have any reference implementation, then we apply differential testing. What does that mean is that we provide the same input messages to multiple devices and observe whether the outputs are same. If the outputs are not same, that means I know that at least one of them is deviating from the standard. I don't know which one, but at least I have some indication. Okay. It may happen that both of them are deviating from the standard. We also found that instances. Now, if you want to apply this differential testing on 5G, you can. One approach is that you generate random inputs and keep doing the random testing and see whether you get output. I mean, different outputs from different devices. But it will be extremely inefficient, because how many times you'll generate any random inputs, and you don't have any feedback because it's a black box approach, right? I mean, you can only see the inputs and outputs. You cannot have any system logs, anything like that from coming out of the basement. And even if you have these system logs, it cannot be applied for all different types of UE basebands. For example, iPhone, it's extremely difficult to get the traces. Sometimes in some cases, you require root access. You need to root the phone and get the system traces, which is not convenient. So we propose that first we'll extract the FSM, find state machine of the product, of the basebands, and we'll see that whether those find state machines, they deviate from each other. And if they deviate, we say that one of them at least non-compliant with the standard. So the high level idea is that we have a FSM inference module which sends inputs to the devices, and then observing the inputs and outputs, it creates the finite state machines. For all devices, we create finite state machines like this. And then we go to the equivalence checking phase, where we pairwise compare the FSMs. And whenever, after doing the pairwise comparison, if we find any trace which is deviating from each other between the FSMs, we call that deviating trace, and that is we use as a proxy for analyzing the non-compliance or deviation from the standard. All right. So I'll quickly go into that this FSM extraction, because this is one of the core part that you can actually use that for other protocols as well. So here you have a learner which is trying to learn the finite state machine, and this is the system under learning that in this case your basebands. Now that sends some messages here. For 4G, it's enable like attach authentication request security command, and we get the responses. So you have some fixed number of input messages and output messages. But the catch is that if you send, it's not that easy that you can send these messages. You have to build an adapter in the middle that will allow taking the input symbol and create a concrete message and send it to the device. So we have actually repurposed srsRAN and really hacked that srsRAN really well to make this adapter, which can now send any arbitrary messages to the device. So it's sort of a SCAPI version of 4G or 5G. Okay. So SCAPI, I don't know how many of you are aware of SCAPI. It's a really handy tool to create any kind of TCP/IP packets. So, but for 4G, we don't have any such kind of feature. So you can create, at least for the downlink messages, you can create any arbitrary messages. You can just have to tell at the high level in messages what kind of fields you want. All right. So we have developed this using srsRAN, and I really appreciate again the SRS team for that. So again, like these srsRAN or hacked SRS, modified SRS, they can create these messages. All right. So there are many challenges. I cannot go all of them, but there are some high-level challenges. Is that you have to identify the input and output alphabets. You have to make a balance between when you want to terminate your learning or how much coverage you want. And of course, there are engineering challenges to develop this adapter based using srsRAN. All right. So here in this case, whenever you have two FSMs, you want to know that whether the FSMs they are same or they are different. So for this, actually, we reduce this problem to a model checking problem. Here, the model checker is very good at finding the counterexamples or deviations between two graphs. So you give same input, and you want to see whether the output of first FSM is equal to the output of second FSM. If not, then it's a deviation. All right, so we evaluated this tool for 14 devices from 5 vendors, and we have identified total 15 deviating or non-compliant behavior, and among them, two are interoperability issues and 11 are exploitable attacks. So I'll show just one of them. Again, like here, once you find the deviation, our tool only help you find the deviation, but it cannot tell that what is the root cause, which property it violated, security property it violated, or how the attack can be formulated. So these steps are still manual, right? Once you get this deviation or non-compliant behavior, you need to do the root cause analysis manually. You need to generate the attack manually. And you have to also validate that in your testbed, which is built on srsRAN. So I'm going to show just one of the vulnerabilities that we have found. For example, booty reallocation command in 4G that is used to change your temporary identifier. In 5G, we have the 5G version is called configuration update command, that message to change your temporary identifier. So here, attack core network, I mean the fuzzer or the DIQE, they tried to send the replay message, but replay message didn't work. The UE actually dropped that message. And then we found that, interestingly, that same UE, it accepted a security mode command replay message. So replay is not allowed at all. First of all, it accepted that replay messages, which is wrong. And then Guti reallocation command replay worked. That means it is vulnerable 2 times. First, it accepted a replay message of security mode command, and then Guti reallocation command replay worked. But Guti reallocation command replay didn't work in the first place. So it's very stateful vulnerability, you can see. All right. So this is the specification. What does it say? But devices are deviating from the specification. Now, how the attack can be formulated. So let's say Guti reallocation command has been sent, but a fake base station on man-in-the-middle relay, they can actually capture that, and they don't forward that message to the EV. Now, whenever there will be a replace security mode command sent by the fake base station, it will also send Guti reallocation command, the previously captured one. And by doing this, the core network and EV, they will be desynchronized with the TMZ. That means core network knows the device TMZ1, but the device knows another TMZ. So they will be desynchronized. And at some point of time, they will keep desynchronized and they will be deprived of any kind of services. So this is sort of a denial of service attacks. Anyway, so this is how it works. So we have like this tool, DIQE. Using DIQE, we have reported all the problems. The CVEs are there, and they have patched. But the question is that how can we use this tool for 5G basements? So of course, 5G has new messages, some new protocol features. That means that will require new input messages or new input alphabets or output alphabets for learner, FSM learner. There are some new logic for the context checker. We have some built-in context checker that if a packet you want to send, but that doesn't actually match with the context, right context, we immediately drop that. We don't have to send that. And also, most importantly, it has some scalability issues. For example, if you have more messages, more symbols, you need more time or more number of queries to learn the FSM, because you're learning the FSM in a black box fashion. You send queries, you get the response, you try to infer the final state machine. But it is hugely time consuming if you have large number of messages, which 5G has. So we are trying to address all of these limitations. We have an initial prototype of 5G version for this tool. But that's actually conclude my second part. Let me give you a very high-level overview that what our lab is working on currently. So we have mainly 3 directions that we are working on: analyzing the design of the systems. Here we have recently we have worked on a system that can take all the specifications written in natural languages, and using natural language processing techniques, it can automatically create a formal representation of that specification. Okay, so let me show you that framework quickly. So it takes these natural language specifications as input on your left-hand side. And after doing all these natural language processing, and there are some formal method mechanism, and using those, combining those, at the end, we create a fine tested machine. Now you can think of that the first part, we say that one expert has to manually read the specifications, and it takes hundreds of hours to create this fine tested machine. Now you get this natural language specification, and using our tool called Hermes, you can actually create the FSM automatically. You can also use this tool to use as a baseline for this die-QE approach. So we have shown that here you can do differential testing, but you can also actually compare. You can compare, if you have a baseline reference system machine, you can compare your any of the devices FSM with the baseline FSM or reference FSM. So this work is, is hugely important, or they can help in many ways. Sorry for the back and forth. Yeah, anyway, so, and some of our work is in the design section, analyzing the design section, we actually apply these formal verification mechanisms and try to develop those techniques. And we are also extensively working on analyzing the implementations, or either in the black box fashion or gray box fashion. And also based on all these insights, our overarching goal is to build a secure solution for the cellular systems and overrun systems. So with that, I would like to conclude. As a summary, like we have in my talk, we have shown that how formal verification, software testing, and program analysis can be applied for secure by design cellular systems. And if we want to apply those for 5G or ORAN systems, there are many challenges. With that, I'd like to thank you, and I'd like to acknowledge the funding I'm getting from NSF, DARPA, Intel, and Penn State. Thank you all.
Thanks very much, Syed. As we're running a little bit over time, if you have questions, I recommend that you seek Syed out in person.